So this is Class Up Your Config, and I'm Andy Scott. I'm a senior software engineer with 47 Degrees. We're a global consulting firm in the UK, Spain, as well as the United States, and I'm from Seattle, so I'm with the US office. We're also the ones responsible for a lot of the conference t-shirts, so if you haven't gotten one and you happen to be one of the smaller sizes, I think we still have some left. So you can head on over to our red booth in the far area of the Commons. So with that out of the way, again, this is Class Up Your Config. We're going to discuss a open source project, a 47 Degrees project. It's called Case Classy, and it's a library centered around decoding data, specifically configuration data. Goals. We're going to talk about the problem that we're trying to solve. I just touched on it briefly, the decoding data. We're going to learn about arrows and some functional programming concepts. We'll talk about them briefly. I'm not going to go into too much detail, and then you'll see these concepts show up throughout the talk or throughout the code that we kind of dive into. We're going to derive or build a solution using Case Classy, so we're going to go through what it takes to implement some functionality using this library. And then at the very end, there's a little bit of a review and some final notes. So, what's the problem? We have configuration data, or at least for production applications or services that we deploy, there's frequently configuration data that you have to load or that we load at the beginning of our application startup. Frequently it looks something like this. It may be, it's usually text. It's typically structured text, but it comes in string form or some kind of unstructured form. And it can contain all different kinds of values that we want to do different things. We want to do stuff with those values. Here's another example. This is actually from Scala exercises, and in some cases our configuration may contain environmental variables or sensitive information like the database information and the user and password. I think those were redacted and I dropped in some dummy versions, so don't try that. And then occasionally we'll override configuration on the command line. So configuration can come in many different ways, and then we load it. And across a lot of the different projects that I've worked on, I frequently run into code that looks like this. This is using type-safe config, extremely popular configuration library in Scala. Who here, just if I can get a show of hands, has anybody used, or I'm expecting most people have used or seen type-safe config? Right. And have you seen code like this, where everybody's just pulling the values out directly? Has anybody seen or encountered that? Right. So that definitely happens. And the risk you run is that any of these values or these calls can potentially fail. So in this specific example, every single one of those lines, if that corresponding configuration is missing, the application is going to fail to start, which is fine. The application didn't start, but we're not going to get we don't get meaningful information out of that. So what we end up seeing is something like this, which isn't tremendously useful. And this particular case is if you're loading some Mongo configuration for, I think, reactive Mongo. So not related to the previous snippet, but still a configuration exception. So that's what we want to solve, or what I want to solve. So fundamentally, nobody really wants to read these stack traces or debug these configuration errors. It's potentially really, really irritating. If a configuration error happens, frequently it's because it's code somebody else wrote, and you have to spend extra time trial error debugging that code or debugging the configuration. And at the same time, very few people, or most people, don't want to spend a lot of time writing good configuration code in Scala. You spend most of your time writing your application, writing your business logic, focusing on delivering features or delivering functionality, and then quality configuration code may come at the end when you have some extra time. It's usually not a focus. So you kind of have this this situation where we want this, but we don't want to spend the time to get it. And so we end up with errors that we occasionally have to debug. So we can build a solution. This is what we want, or kind of what I want. I want an easy-to-use API, so beginners are able to use this library. Want Scala as a first-class citizen. I think a fair number of people use type-safe config. That's a Java library, so it works well in Scala, but it's not a Scala first-class citizen in my mind. because we want to avoid throwing any exceptions. With that in mind, we'd also really like to have descriptive errors that tell us exactly what's wrong, and ideally tell us everything that's wrong, or as much as we can know at any given point in time. And then we would also like a minimal, no or minimal additional dependencies to our build. Again, configuration is kind of tacked on at the end, or an afterthought, so we don't really want to bring in a whole bunch of extra libraries to do this. We want it to be out of the way and not interfere with the rest of our work. And then my goal is to have a purely functional implementation. So even if you're a beginner and you don't know functional programming, you can still use the library, but behind the scenes, it's using functional programming principles and follows those. So, little spoiler alert, we're going to look at some configuration and some examples using case classy before we actually dive into building a solution. So you're going to get to see what you can do before we actually go through the motions of doing it. So here's a sample config. It's extremely simple. We have two service backends that we'd like to communicate with. We have a user's service and then a database that we need to communicate with. And both have a host and a port. And to load that with case classy, following the name case classy, we're going to define some case classes that model our configuration, and then we're going to quickly load the configuration data, that raw text, directly into those case classes. In this particular example, it's using typesafe config behind the scenes. So you see that I import classy.config that binds case classy to typesafe config. And we're able to quickly generate a decoder for our configuration and load that config. And if you notice, I don't actually import com.typesafe.config anything. Case classy has built-in helpers so that you can load those things directly. Frequently, we load configuration from the class path, and the .load command at the very end loads the file directly off the class path. Now we're going to take the same exact snippet of code, and maybe we don't want to use typesafe config. Maybe we'd like to use a different backend. So almost the same exact piece of code, but now we're loading Java properties directly. So if you're running on the JVM, you get this functionality automatically. The only dependency that would be required is case classy, and then if you want the automatic derivation, this pulls in Shapeless. So same snippet of code, just changed slightly, and we're loading Java util properties. If the decoding fails, you can see that the result is an either. So on the left-hand side of that either, there's a decode error, and that's going to capture the failures that occurred when the configuration failed to load. And we'll see more about that in a minute. And a final example, this one you get to see a tiny error coming out. Foobar, we have a sealed trait and a couple of distinct subtypes of that. We load some data, and the data is incorrect. In this particular case, it says that there's multiple errors. It's missing a value at path foobar, and then at list foobar at index 0, it's also missing some values. So you can see that it collected all the different errors that occurred and presented them to you, showing you specifically what happened at each different path. And I know there's a little bit cut off, but that's good enough. So, cool. We're going to go through and build the solution using case classy now. So, but first we're going to do a little bit of background information on some FP concepts. First things first, algebraic data types. These are sum or coproduct and product types. You may have heard the term. I think most people have heard this term by now. But you've definitely used case classes. So you've used tuples and you've used case classes. Those are your idiomatic or your common product types where you have multiple values and they all have to exist together. And then we also have coproduct types, which typically are sealed case class hierarchies or disjunctions like Scala either. Maybe Scala.util.either, that might be a typo. Either way, Scala.either is a disjunction of two different types. You have one or the other. So that's a coproduct type. And then case class hierarchies, as you just saw earlier. Case classes and case classy ADTs. So for case classy, how do we use ADTs? Well, we model our configuration as case class hierarchies, like we saw before. We decode raw configuration into those ADTs, and that can come from the Java properties, the typesafe config, or other data sources. And we also capture our decoding errors as an ADT. You saw a snippet where it had a decode error on the left-hand side of our either. That is an ADT that's built into case classy, and it captures all of the semantics of what happened with your decoding failure. Cool. Arrows. So I ripped this from Wikipedia. It says, arrows provide a referentially transparent way of expressing relationships between logical steps in a computation. Arrows are also morphisms. You don't need to know any of that. What you need to know is that arrows are structure-preserving functions, and you already know what functions look like in Scala. So here's a simple arrow from an option of a string to a list of a string. And throughout the rest of the slides, you're going to see this notation where I just use a single arrow instead of the function arrow from Scala. So this is an arrow from option of string to list of string, and that's what it's going to look like going forward. Arrows, just like functions, can compose. You can join them together and do a lot of different operations with arrows. So if you have an arrow from an int to int that multiplies an integer by 2, and if you have an arrow from int to string that does some kind of two-string function on that arrow, then you can compose those arrows together using basic combinators like and then. So arrow 1 and then arrow 2 is going to give you an arrow that takes the input and passes it through both and then gives you the final output, just like it would for a function. And this is just vanilla Scala functionality right here at the bottom. All right, I think we're ready. So arrows in case classy, or the most fundamental part of case classy is decoder, which is an arrow from some input type to either a decoding error or a result type, a desired result type. In arrow notation, this would be A to decode arrow or B. And if you can imagine, if we try to join these together or take multiple arrows where the result is a decode error, that's going to be a bit tricky. So there's this notion of a Kleisli arrow, which allows us to pretty much treat this as an arrow directly from A to B. So instead of having to worry about the error behind the scenes, we can just simply compose these arrows together, and we're going to get error and error handling semantics automatically. So if something fails, the whole computation is going to fail automatically. And we get that by using Kleisli arrows. Or rather, decoder from A to B is effectively a glorified Kleisli arrow. We don't actually reference Kleisli arrows in the project. How do we create a decoder? Excuse me. On this, you can see that decoder has a single apply method that is not implemented. In case class C, that's exactly how it is, and there's also a lot of final implemented methods that give you all the combinators to build up your decoder from your input sources. So with that in mind, to create a decoder, we just need to pass in or provide a function from from an input type to our result, which is either the error or the result type, and we're able to create a decoder using this instance helper method. So if we wanted to decode a string to UUID, which is pretty common for applications, we can rely on the Scala try and the Java UUID to parse the UUID and then catch any exceptions that may occur, since our Java methods frequently throw exceptions when things go wrong. So here we're decoding an input value. We're converting that to an option because we don't care about the actual exception that occurred. We know that any exception for parsing a UUID means that the parsing failed. We convert that to an option, and then we convert that to a right-hand side either, with the left-hand side being a decode error saying that the UUID was an unexpected value. And then quickly some examples. You can imagine that hello and world don't load. This third example, turns out that UUID, that's not a UUID, it's a little bit short. So you can see that we don't have any way to know exactly how short, but that it reports that that was the wrong type and the input value was that underlying string. And then finally we have a valid UUID that we can load. Composing decoders. So just like we did with the basic Scala functions, we can compose these arrows. So if we have a decoder from type safe config to string, and then we use our decoder from string to UUID, we can then decode from config to UUID. So we're going to read a value from our configuration at path ID, and then we're going to decode that to UUID. And you can do that by just calling the and then method, just like you would on chaining Scala methods together or functions together. And then if we actually run that, you can see that it reports things are wrong. That one works. Continuing with composition, let's see. I mentioned earlier that built into case classy there was different helpers for type safe config. If you already have the decoder from a type safe config to a string, you can also load type safe config directly from string, and there's a helper .fromString, which essentially takes an arrow from string to type safe config. So it loads the type safe configuration for you, catching any exceptions in the process, and then composes that with your existing arrow. So your existing configuration gets appended to the end of that computation with the decoding from the raw string to the configuration with type safe config at the beginning of that computation. So here we're calling decode string and just loading a string directly using type safe config. So type safe config does the dirty work of parsing that, loading that. It may throw an exception, and then if it succeeds, it eventually goes through our little arrow flow. Now, decoding type safe config it's been done before. There's a number of libraries that do that already. Case classy is built around arrows, and we can have alternative or different input sources. So we're going to go through what it takes to decode a map of string. And this is already built into case classy, but we're going to derive it through this talk, or derive parts of it through the talk. So we're going to decode map string decoding, or we're going to build map string decoding from scratch. This is useful because system.environment properties as well as Java properties files all can be converted to or go directly to a subtype of map. So you're able to load those conveniently if you have a decoder for map string. First thing we're going to do is we're going to write a quick helper function that lets us pull values out of the map, and then a quick decoder for pulling values out of a map. This helper function has a final parameter f of string to, oh man, it's cut off in this resolution. No, that's okay. So we're pulling values out of a map, and we're going to have an additional helper function that will do any final processing on the values coming out of the map, and we're going to handle any exceptions that occur in that final processing. So if we want to decode a string out of the map, we're just going to read values directly out of the map, map.get to write, and then we're wrapping the identity, we're using the identity function for any final processing, but we wrap that in exception handling. So if there's an exception that occurs when that value is decoded from string, we're capturing that there and turning that into a decode error. Obviously, decoding a string from a map string is not going to throw any parsing exceptions. It's just going to work or not work if the value is not there. But for other cases, like decoding a long or Boolean, those values may parse or fail to parse, in which case you want to capture those exceptions. So our helper allows for that. So here we just built up a bunch of arrows from a map string to long, to string, to double. And we're able to do that very, very easily. And then we can, of course, call that, or build up, decode foo long, decode long from map. We can call those and get the different results. So decode foo long, we're going to pull the value foo out of our map and decode it as long. Obviously, in this first case, it fails because that key isn't there. And in the second one, the foo value is there, but it was unable to actually parse the value. So you can see that the exception that would have been thrown when when we parsed the string to a long, that exception was caught and turned into an error type in our error ADT. And then finally, we have two values that work. So how do we get to ADTs? How do we get to our case classes? We already have a decoder from string map to long that reads at path foo. We also already have a decoder from string map to string that reads at path bar. We want to join those together and do both at the same time. And we can do that by fanning out those two arrows. So if we take string map to long and join it with string map to string, we're going to get a string map to a tuple of long and string. And it's going to collect the errors in the process. So here we use the helper method join that joins those two arrows together, or those two decoders together, and gives us a decoder for our tuple. And then we can take advantage of the tuple constructor on case classes in Scala and just map our result directly to that case class. So now we have an arrow from string map, or a decoder from string map to foobar. Continuing with this, we're just going to load some different values. If you load an empty map, here you can see that it knows that at a nested path, it's missing the value bar. So it's expecting, or excuse me, yep, at path foo, it's missing a value, and at path bar, it's also missing a value. So it's captured the fact that both of those things are missing. If you provide 1, it's going to tell you, or if you provide a wrong value for 1, it'll tell you that that value is wrong. And then, yep, wrong type. And then finally, if we provide 2 correct values, or correct values in our config, it's able to load that correctly. What if we want to load nested paths? I mean, our goal would be to load into nested case class hierarchies or more complicated case class hierarchies. That means we need to be able to load nested paths from our string map. Any ideas on what you would do for this? Nope. Right, so what we want essentially is to first decode from string map to another string map. We're going to strip out the prefixes. So let's say you want to decode something at path foo.foobar. You want to first filter that map, stripping out the prefix, and build a decoder that does that prefix stripping for you. And that's exactly what we're going to do. And we're going to be able to do things like this, where we first decode map for map at path foobar, and then we actually load our case class from there. And this is how that's implemented. If you wanted to actually implement that yourself, you would load the value, convert the map to a list of string, filter all the keys, and then go back to a new map and wrap it up as a decoder. So here you have decode map for map. It takes an input string, which will be the prefix for where you're trying to decode. It's going to find all the keys with that prefix, strip the prefix off, and then give you a new decoder that operates on those sub-values. And this is not the most efficient implementation of that. It's just a implementation of that. If the final map is empty, so if it filters and finds no results, it's going to tell you that the values are missing. Otherwise, it gives you the filtered results so that any other errors can be handled by decoders that occur after that. So we can use this, and in the spirit of all the previous slides, we have examples of using it. First one you see missing values. Next one you see a successful loading. So we've loaded nested values or a nested map from our overall map, and then we pass that off to our decoder for our case class. So we're going to do some housekeeping. If you look right here in the middle, we do decode map for map, foobar, and then passing it off to our next decoder. That's pretty clunky. Nobody really wants to write code or I don't expect people to build up their decoders that way. It'd be really convenient if we could take our existing decoders and simply say that we want them to decode from a nested path. And we can do that by leveraging type classes and some implicits. We're not going to go through implementing those, but if they were in place, or if they are in place for the source that you're decoding from, you can simply say, I want to take my decoder from my case class and decode at path foobar, and it's just going to work. And so behind the scenes, there's an implicit instance of this read type class that expresses the ability to read from a structure and return another structure of that same type. So here we can read a string map and then get another string map as a result. Yeah. And that simply wraps our underlying decoders. So it's a type class that captures the ability to read values at a path. We can continue to housekeep. We can use our type class to summon instances for reading different values. So instead of having to build up all that stuff by hand, if it's already in place, we can just say we want to read a value from our string map at path, or read a value foo, read a value bar. We want to join those together. We're going to map that to our case class, and then we're going to decode at a nested path. And on the right, you see in arrows exactly what's happening. We have a string map to long. We're fanning that out with string map to string, which gives us string map to tuple of string and long. We're mapping that to our case class, and then we're decoding at a nested path, which gives you an arrow of the same type. Yep. Great. And this is still a lot of work. You can go through that if you'd like. But in many cases, we just want it to work. You saw in the very first few slides that we had some case classes, and with one line, we're able to load those case classes from different data sources, and that's done with Shapeless. So if you import the generic package from case classy, which is from a separate SBT project, so separate dependency, then you get Shapeless driving all the decoders for you. It's doing all the work of building up the decoders using all these different combinators that we just went through. So instead of doing it by hand, you just say derive decoder from string map to foobar. It doesn't know that you want to decode a nested path, so you still have to tell it to do that, but it's done most of the work for you. Cool. So what have we done? We've built decoders from a map, and that used arrows. We've built decoders for reading nested data, and we kind of dove into arrow composition there. So fanning out arrows, as well as fanning out arrows and then mapping the results. We decoded a case class, With decoding a case class, we did the fanning out of arrows and then mapping it to the case class. And then we made decoding cleaner with implicit type classes. That was the read type class. And then finally, we used Shapeless to derive the decoders for us. So we put Shapeless behind the wheel and said, do the work. We don't want to do this. And why would we want to do all this? I showed you some more simple examples. This one's a little bit more complicated. Here we have sealed abstract class shape. There's 5 different distinct kinds of shapes in this hierarchy. They all have different values that they expect. And then we want to load a whole list of these shapes. And we want to know exactly what goes wrong, if something went wrong, and then we want the result just to appear. To get the decoder for that, using Shapeless, using the generic package, you can just ask to derive a decoder from config to shapes, and it's going to build that up for you. That includes handling lists, handling the errors for multiple items occurring at the same time, and all the different decoding for all the different subtypes of shape. So it derives all of that for you automatically. And what does that look like in practice? If you have passed in some configuration, here's a sample input configuration with some valid and some invalid entries. So the first, you can probably figure out which ones are valid or invalid, but the first one is valid, second one's invalid, I believe the third one is valid, and then the fourth one is obviously invalid. And it's index 0, so you're going to see on the left the ADT representation of that error, and on the right is a human-friendly version of that same error. So you can see that at index 1, at index 0 it succeeded. It was able to load the circle with radius 2. But at index 1, it noticed that we had rectangle. It tried to load values at the path rectangle. It couldn't figure it out. And it also tried all the other alternatives. And it reports exactly what went wrong with all those alternatives. So for circle, rectangle, or regular polygon, square, and triangle, it didn't get very far. For rectangle, it got a little bit further because you provided the key. There's a key for that. And then also at index 3, it failed, but there's no real value to showing the extra error. And again, on the right, same representation, just a human-friendly printout. Some features and other miscellany. This is Scala 2.11 and 2.12 at the moment. It also supports Scala.js, and that includes supporting type-safe config, or this library Shocon, which is class path compatible with type-safe config. So if you want to load Hocon files on Scala.js and on the JVM, you're able to do that, and you're able to do it in a generic fashion using case classy. The project is modularized, so the core module has no external dependencies. All the FP concepts are built into the library, kind of under the hood, when they're used. And they're not exposed out of that. If you want to use the type-safe config library, there's a module for that. If you want to use generic derivation, there's a Shapeless module for that as well. So the core module has no extra dependencies. And then finally, this is also a type-level incubator project, which means there's a code of conduct and some standards regarding the documentation, website, and maintenance of the project. So we're maintaining this at 47 degrees and type-level incubator. Next steps. So configuring derived decoders. I showed automatic derivation. It's possible to specify different options for how those decoders behave, even when they're derived automatically. And there's some options already built in. Actually, if you go On this slide, you can see that it's automatically looking at a nested field in your list of shapes. Maybe you want to discern the different types by having an additional field called type that says type equals shape, or type equals circle, or type equals rectangle. It's possible to have the generic derivation accommodate for that by passing in a different flag. And so that's already built into the library. It's just not covered in the examples here. My goal is to add more options on an as-needed basis so that you can customize how your case classes are loaded as you please. Looking to support decoding more input types. Right now it supports Java properties files, loading files that are property files, supports type-safe config, it supports showcon type-safe config, but it can support any kind of data type. It could support binary data types. It's completely indifferent because it's built on the decoder, which is essentially the Kleisli arrow from an input type to the decoded result. And then finally, we're planning to integrate with Freestyle, which is a framework for doing functional programming in Scala. And that's at freest.io. And that was it. Got through that fast. Yeah, that's not too bad. Any questions?
Hello.
Hi.
I also wrote a Java configuration library for my project back in the days. And what we used in there heavily is configuration reloading on runtime.
Mm-hmm.
Is this case classy also supporting configuration runtime? Like, for example, when a file on disk is been modified, it will reload it?
So the question was, I was asked to repeat questions,
Yeah, sorry.
No, it's fine. The question was, does it support configuration reloading? And there's nothing built in case classy right now for configuration reloading. It's meant to be immutable, so you're loading whatever your data source is to an immutable result, or typically an immutable result. There's nothing that would prevent you from running the decoding process again or automating that whenever files or configuration changes. But you're going to get a new case class representation of that data that then you can hand off to your application. So
yeah, I just
there's
rebuilt
no facilities in the library as it stands. But there would be some room for automating some of that. The goal wasn't to handle any changes, any mutable values at like the value level. So imagine a whole hierarchy of configuration. If you want to handle reloading of specific values or notifications for changes of specific values, that's out of the scope for this project. So, did that answer the question?
Yes.
Great.
Hey, quick question regarding the configuration in general. So, you have your KC, whatever, like, right, you have your data configured, and then you want to update that at scale. Let's say you have like a gazillion of machines and you want to update configuration on all of those, like, what do you do, like, how you usually handle this kind of thing?
Redeploy all your servers.
Redeploy everything?
I think that's a team decision in a way, isn't it? I mean, on some of the work I'm currently doing, everything is immutable, and so we are doing all container-based deployments, and we'll simply just redeploy the container.
Right. So that's the pattern I usually see. But then, wouldn't it be easier to just have case classes with the values directly without reading them from files? If you every time you pretty much redeploy, you can update the code, rebuild it, redeploy. So what's the point of using like fancy libraries? With and then you have to deal with the errors somehow, right? But if you have like case class, you have like service, whatever, host, port, and you have to provide that at compile time. It's verified by the compiler. So if you need to change it, you redeploy again, which is,
I think I follow. I mean, there's nothing that would prevent you from using this at compile time to validate configuration. I mean, I've currently only used this at runtime, at the boot of applications.
Yeah.
So if an application is going to fail, it just reports that it's failed. But you could validate configuration ahead of time or load configuration ahead of time, and maybe generate static configuration from that that is guaranteed to work. But I don't have that specific use case. In terms of reloading configuration, or one thing I'm looking at is on some work I'm doing, we have the need for reconfiguring logging levels for debugging on the fly, or boosting trace levels. And so I may look at adding some functionality to this to make it easier to get notified when something changed. I mean, again, there's no plans to support individual fields or values changing, but if you want a whole configuration file or a whole set of config to kind of reload or to change without redoing your whole environment, then that's something that I personally need. So at some point that will be addressed. I don't know if I answered your question or not.
Yeah, thank you.
Yeah, so this is what you described is all for configuration that is required. So what if I want to fall back on a default of a value?
So option decoding in the case classes, if you mark a field as optional, then it won't actually fail if that value is missing. I mentioned that there's the ability to specify options for the derived decoders, and I think I did a pull request or a PR for this. I'm not sure if I implemented it fully yet, but with Shapeless, it's possible to pull off the default values from case classes. So if you wanted to specify your default values in the case class as default parameters, or default parameter values, then that is low-hanging fruit in terms of functionality for case classy. If you wanted to specify your default values elsewhere, I can go back to, it's not shown, but I mentioned that there's tons of methods implemented on decoder, final implemented methods. There's fallback methods where you can specify a fallback for your configuration. So if the decoding fails, it will just go to this other decoder or go to this hard-coded result. And you can do that at any level of your configuration. So what I typically do is, sure, you can drive your decoder automatically for the whole configuration universe, but what I typically do is decode the parts that I know I want automatic and maybe specify a default value for that, and then decode the rest. So I'll kind of drive the automatic derivation and insert my default values or guide it a little bit where I need to. But yeah, there's support for defaults and fallbacks.
Okay, thanks.
Yep. I think that's it. Thank you guys for coming. Hope you enjoy the rest of the conference.